Today we are going to learn in this module about some of the following things. In the earlier module, you have learned two applications of chi-square distribution that concerns the population variance. In this module, you shall be able to learn the other two applications of chi-square distribution that are related to hypothesis testing of two situations. First situation is know whether a given sample can be taken to have drawn from a population with a specified distribution called the chi-square goodness of fit test. The second situation is where we would learn whether in a joint response to the two categorical variables, can the two categories be regarded as independent of each other, termed as chi-square test of independence of attributes. So let us now discuss about the chi-square test for goodness of fit. Sometimes we are interested in knowing whether a particular random phenomena can be explained by fitting some specific probabilistic model. In other words, we wish to test whether a particular random sample can be considered to have drawn from some specified probability distribution, say the exponential, the normal, the Poisson, or some other distribution. For example, we may a priori expect number of typological errors per page in a manuscript to constitute a sample from a Poisson distribution, or occurrence of 6 in throwing off an unbiased die to follow a uniform distribution. Now this can be tested by observing the actual number of typographical errors per page in a manuscript, or by recording the outcomes in a large number of throws of a dice or a die, and then testing whether the assumption about the underlying distribution is realistic or not. The statistical tests that determine whether a given probabilistic model is appropriate to explain the random phenomena under study are called goodness of fit tests. A goodness of fit test is a statistical tool that examines how well the assumption regarding the specified distribution fits the random phenomena under investigation. It tests whether our data supports the assumed distribution regarding the random variable. Now this is based on a test statistics that follows the chi-square distribution. To illustrate the procedure, we take a very simple example of tossing a die. We know there are 6 possible outcomes which could be denoted as x, and the probability of each outcome is equally likely if the die is an unbiased one, because the number which you may get could be from 1 to 6. So we hypothesize that it is a fair die. This is same as theorizing that distribution of outcomes follows a uniform distribution. If so, we can write the frequency or function fx is equal to 1 by 6, where x takes the values from 1 to 6. Now suppose the experiment of tossing of a die is carried out 150 times. Each time the outcome is noted and it is recorded in the table as observed outcomes. It is called, or it is also defined as observed frequency. So in the table we have the observed and we can find out the expected frequencies. So they are both mentioned here. So you can see in the first row we have the observed outcomes and we have the expected outcomes in the second row. And we have the outcomes from 1 to 6, 1, 2, 3, 4, 5, 6. Now once we have this table or these frequencies, then based on our hypothesis that it is a fair die, if it is true, then theoretically we would expect each outcome to occur 25 times. 25 we obtain from 150 divided by 6. The theoretical outcomes are recorded in our table 1 as expected outcomes, as I mentioned earlier, and they are also defined as expected frequency. Now conventionally, each possible outcome in the experiment is referred to as a cell. Accordingly, the notations OI and EI are the observed and expected frequency, of the ith cell respectively. In our example, there are 6 cells, therefore I ranges from 1 to 6. Also, there are 5 degrees of freedom because only 5 cells observed frequency can be freely determined. If the observed frequency of 5 cells is known, then the 6th cell is equal to the total frequency minus the sum of the frequencies of the rest 5 cells. That is why we say that the degree of freedom is 5 cells. I hope you understand this concept of degree of freedom. Now we can see from this table that there is a discrepancy between the observed and expected outcomes. In order to test whether the distribution of outcomes is uniform or not, we need to compare the 2 types of outcomes and find whether the observed discrepancy, which is defined as nothing but OI minus EI, is on account of the sampling fluctuations, or is it due to the die being a biased one. To test this, we compute a test statistic whose sampling distribution for sufficiently large number of observed frequencies is approximated by chi-square distribution with k minus 1 degrees of freedom and is defined as chi-square is equal to sigma, which is summation I is from 1 to k, and this is over OI minus EI square upon EI. This is our equation 1. Now in this way our I ranges from 1 to 6, and in terms of notations k is equal to 6 and degrees of freedom is equal to k minus 1, which is equal to 5. So if the discrepancy OI minus EI between 2 frequencies of the ith cell is small, the computed chi-square will also be small. I'm sure this is obvious from the formula. Now this would imply that the 2 frequencies are quite close to each other, which means the observed and the expected frequencies are very close to each other, and we would then conclude that the die is unbiased and the outcomes are uniformly distributed. Similarly, if the discrepancy is large, it means the computed chi-square will also be large, implying a substantial difference between the observed and the expected outcomes. As a result, we would conclude that the outcomes of the experiment under consideration are not uniformly distributed, and the die would be considered as a biased one. Therefore, the next obvious question is, at what level of the computed test statistic is considered large? Now, this in turn depends on the significance level alpha. I am sure you are all familiar with this concept of alpha. It is alpha level that would give us the critical values for a given degrees of freedom for the rejection and non-rejection reasons. The steps in the testing procedure are therefore explained below. The first step is define the null or H0 and alternative hypothesis HA. On the basis of our assumption under the null hypothesis, we compute the expected frequencies of different cells. Then our third step is compute the discrepancy between the observed and expected frequency for each cell, and then find the square of each discrepancy, which means find the square of OI minus EI. Now each of the square discrepancy is then divided by the expected frequency of the corresponding cell to obtain OI minus EI whole square divided by EI, which is called the relative discrepancy. So we try to divide by EI so that we have a normalized value of this discrepancy. Now sum of all such computed ratios over each cell, that is our next step. The sum of all the ratios gives us the value of the chi-square test statistic with nu equal to k minus 1 degrees of freedom. I am sure by now you are familiar that we define this degree of freedom by the symbol nu. Now, if the significance level is alpha, the critical value is denoted as chi-square alpha nu. It is important to understand here, since only the large discrepancies between the observed and expected frequency makes distribution a poor fit to the given data, the rejection reason lies to the right hand side of the distribution. I'm sure you know that chi-square distribution is a right-handed kind of a distribution. So consequently, only the right-tailed critical value is considered for the test, which you can make out from our figure. The question therefore is, what is the decision criterion? The decision criterion is that reject the null hypothesis if the computed chi-square test statistic is greater than or equal to the critical value, which is known as chi-square alpha nu, and do not reject the null hypothesis if the computed chi-square test statistic is less than the critical values chi-square alpha nu, which is a corollary of the first one. Now I am sure you can make out that if hypothesis is not rejected, we conclude that the fit is a good fit and the discrepancies present are attributed to sampling fluctuations. On the other hand, if hypothesis H0 is rejected, we conclude that the fit is a poor fit and the discrepancies are not due to sampling fluctuations, rather are due to poor fitted distribution. So if you look at the diagram, you can see that we have the rejection and non-rejection reasons for this chi-square test in our figure, and the upper tail area, which is the shaded area, is equal to alpha, and we have the curve which is also known as the density curve. Now we calculate the chi-square test statistic in the above example, which is given in our table. What is our null hypothesis? It is that the die is balanced or unbiased, and the alternative hypothesis HA is that the die is not balanced or is biased, or the H0 is equal to the outcomes in the experiment of tossing a die follow a uniform distribution, and the alternative hypothesis HA is that the outcomes in the experiment of tossing a die follow a uniform distribution. You can see in table we have the outcomes in the first column, then we have the observed frequency, we have the expected frequencies, we have the discrepancy, then we calculate the square discrepancy, and finally in the last column we calculate the relative discrepancy. The values are before you for each outcome from 1 to 6. And once we calculate these values, we can take the sum of the values in the last column, which gives us chi-square and comes out to be equal to 3.36 with degrees of freedom nu equal to k minus 1, which is 5, I think, as we have said earlier so many times. So at alpha equal to 5%, the critical values is chi-square at 5%, which is 0.05 with 5 degrees of freedom, and it comes out to be equal to 11.070 from our table, which are also given in the appendix A5. And once you find out how to look at these critical values, I am sure our next step becomes relatively easy. So if you compare the computed chi-square, which is equal to 3.36, we find it is less than the tabulated value or the critical value of chi-square, which is 11.070. And therefore, it lies in the non-rejection reason, and the null hypothesis is not rejected. Therefore, we conclude that the die is a balanced one, and the outcomes in the experiment follow the uniform distribution. Now, it is a good fit distribution, and the presence of the discrepancies between the observed and the expected frequency can be accounted to sampling fluctuations. Let us now try to understand the checking assumption regarding the goodness of fit test. So before applying the test, it must be kept in mind that this chi-square test should be applied only when all the expected frequencies are large. It is customary to consider an expected frequency small if its value is less than 5. In such cases, the cells adjacent to the cells with low expected frequencies are merged to produce expected frequency of each cell more than 5. Now, such merging of cells results in all the expected frequencies sufficiently large to conduct the test accurately. However, it also brings a fall in the number of degrees of freedom. We would give another illustration to explain the goodness of fit test in such situations. So let's take an example 1, in which we have the data which is given in table 3, which gives an account of number of accidents per day over a period of 150 days. Can the given random variable, which is number of accidents per day, be assumed to have a Poisson distribution? That is our question, or in a way you may say the null hypothesis. So in this table we have the number of accidents, which are the observed frequencies, and the number of accidents which we have taken are from 0 to 5, and you have the corresponding frequencies, which varies from 45 to 6. Let's look at the solution of this example. The solution is that H naught is denoted as the Poisson distribution fits well in the given data, which basically means that the number of accidents per day follows a Poisson distribution. What is the alternative hypothesis? It is that the Poisson distribution does not fit well in the given data, which basically means that the number of accidents per day does not follow a Poisson distribution. Next step is to calculate the expected frequency, expected as according to the Poisson distribution, the equation of which is given as probability x as a function of lambda, which is equal to e raised to power minus lambda into lambda raised to power x upon x factorial, where x is equal to 0, 1, 2, 3, 4, 5. And lambda, I am sure you know, you can recollect from your earlier modules, is nothing but the average number of accidents per day. Now, since the population parameter lambda is unknown, it is to be estimated from the sample data. Applying the formula of average, we can find out that the total number of accidents per day comes out to be equal to total accidents recording during 150 days divided by the number of days. So how do you find it out? We multiply each outcome with the corresponding frequency and divide by the number of days. This comes out to be 0 into 45 plus 1 into 35 plus 2 into 29 plus 3 into 25 plus 4 into 100 plus 5 into 6 divided by 150. So this is equal to 238 upon 150, and therefore we get a value of 1.6. So our lambda is now equal to 1.6. Now, using table A.6, which is given for Poisson probabilities, with lambda equal to 1.6, we obtain the probability for each value of x in our table. You will find in this table A.6 that the probability is up to x equal to 8. Now, to make the sum of all probabilities equal to 1, we add the Poisson probabilities from x equal to 5 to x equal to 8 and write this against x equal to 5. So which means all values equal to or greater than 5 are summed together, and we get a value of 0.0236. So in order to obtain the expected frequency of each cell as shown in column 4 of table, we multiply each corresponding Poisson probability, which is in column 3, by 150, which is the number of total accidents. Further, since the expected frequency of the last cell corresponding to x equal to 5 is less than 5, we combine the last two cells corresponding to x equal to 4 and x equal to 5 of the observed as well as expected frequency. As a result, we are left with only 5 cells. So you can look at this table. I can briefly explain this table where we have the observed frequency, we have the Poisson or expected frequencies from the Poisson probabilities. Then we have the expected frequencies and after we have especially merged, if you look at the fourth column, we have merged the value of the last two cells and we get new value which is 111.805. And in our next column, we have the discrepancy between OI minus EI, or OI and EI. And in the next column, we have the discrepancy squared and the relative discrepancies. So to test whether the Poisson distribution is a good fit in the given data, we need to find the discrepancies between the observed and expected frequencies and compute chi-square test statistic using the formula which we have given above in our equation 1. Chi-square is equal to sigma or summation of I over 1 to k into OI minus EI whole square upon EI, where I, as we said now, is equal to 1, 2, 3, 4, 5, and k is equal to 5 in this case. The computation of discrepancy between the observed and expected frequencies, the square discrepancies and the relative discrepancies are all shown in your column 6, 7th and 8th respectively in our table 4. The sum of all the relative discrepancies gives the required chi-square test statistic and is now equal to 15.73899. Now to know whether this value lies in the rejection or non-rejection region, we require critical value of the chi-square test statistic, which in turn requires information on the degrees of freedom and the significance level alpha. Now in this illustration, the number of degrees of freedom is equal to the number of cells whose expected frequencies can be determined independently, which is 5 minus 1 equal to 4, minus the number of parameters estimated from the sample data. So in our illustration, we have estimated only one parameter lambda, which is the mean from the sample data. Therefore, the degrees of freedom nu is equal to 3. So assuming alpha equal to 0.05, which is 5%, the critical value of chi-square alpha nu is equal to chi-square 0.053 equal to 7.815. Now since chi-square, which is our computed chi-square, is 15.73899 and is greater than chi-square, which is our critical value equal to 7.815, it lies in the rejection region. We reject the null hypothesis that the Poisson distribution is a good fit in the given data. Rather, we find that the observed and the expected frequencies are not in close agreement and the difference between them is too large to be attributed to the sampling fluctuations. Now, it is essential to notice here that in order to perform chi-square test, if some parameters are to be estimated from the sample data, then this entails a further loss in the degree of or the degrees of freedom. For example, for Poisson distribution, one parameter lambda is to be estimated, and for normal distribution, two parameters mu and sigma square are to be estimated from the sample data. Therefore, the formula for degrees of freedom is modified as, for chi-square, degrees of freedom is equal to the number of freely determined cell frequencies, which could be written as k minus 1, minus the number of independent parameters estimated from the sample, which could be written as m. So in terms of notations, we can write down degrees of freedom is equal to nu equal to k minus 1 minus m. Now, having learned this, let us try to understand the importance of the goodness of fit test. I am sure you know that many statistical tests are based on the assumption that the sample is taken from a population that follows some specified distribution. For example, T distribution, F distribution are used only if we assume that population fulfills the assumption of normality. Using goodness of fit test, we can test the same and then apply the most appropriate statistical tool to the given problem. So let us now try to understand the chi-square test for independence of attributes in this section 3. So in this section, we would learn another important application of chi-square distribution where each individual observation in a sample which is drawn from a single population is classified with respect to two categories. Here, we test a hypothesis that whether the two categorical variables or attributes are associated with each other or not. For example, whether a person's choice for movies categorized as action, comedy, romantic, or adventurous type is related to person's gender, male or female, or whether the blood groups O, A, B, or AB type, etc., are related to Rh factor, positive or negative. These are some of the examples where we can apply this. So if the two variables are not related to each other, they are said to be independent. But if they are related to each other, they are called dependent variables. The chi-square test statistics is also used to find whether the two categorical variables are independent or not. The variables being dependent does not necessarily imply that there exists a cause and effect relationship. Rather, it simply implies that there is an association between the two. So I hope you understand clearly the distinction between association and a cause-effect relationship. Now, to explain this, we make use of a contingency table having rows and columns. Now, since there are two variables, one categorizes the rows and the other categorizes the columns. Now, depending on the number of classifications of each variable, the size of the table is denoted as Ri into Cj, where I and j are the number of rows R and columns C respectively. So suppose we wish to test whether the taste preference for different varieties of chocolate, let's say white, brown, and dark brown, are gender, male or female specific. The contingency table, so now you can see that we have variety of chocolate on the one side, and we have the gender and male and female as another attribute. So we have white, brown, dark brown, and the last column gives you the total of all these. Similarly, we have the genders in the rows as males and females, and we have the total in the last row. So the row variable is the gender of the person having two classifications, and the column variable is the varieties of chocolates having three classifications. So the size of this contingency table could be defined as 2 by 3, and it has therefore 6 cells in total. The values written in each cell are called the cell frequencies or observed frequencies, denoted as Oj. The sum of cell frequencies of each of the columns and the rows are called marginal frequencies. For example, R1 is the marginal frequency of the first row, which in this example you can see is equal to 40 plus 45 plus 35 is equal to 120. Similarly, C1 is the marginal frequency of the first column and is equal to 40 plus 40 is equal to 80. And O11 is the cell or observed frequency of the cell with first row and first column and is equal to 40. Now, in general, we can write Ri is equal to marginal frequency of the ith row, where I in this case is equal to 1 and 2. Cj is the marginal frequency of the jth column, where j is equal to 1, 2, 3. And Oij is observed frequency of the cell with the ith row and jth column. Now, suppose we wish to test the null hypothesis that if the two attributes gender and chocolate preference are two independent categorical variables against the alternative hypothesis that the two variables are not. The first step in this procedure is to find the expected frequencies for each cell. Now, what we are given in table are the observed frequencies for each cell. How do you find out the expected frequencies? The expected frequencies are the values that we expect in each cell if the two variables are independent of each other. On comparing the observed and the expected frequencies, we would conclude that the two variables are independent or not. Now, if there is a large difference between the two types of frequencies, as we said earlier, we would consider it as an evidence of two variables being dependent, and if they are similar, the two variables are taken to be independent. So how to calculate expected frequencies for each cell is an important question which we have to understand. Now, before I proceed further, we will understand how to determine the probabilities related to different categories from the contingency table. For example, the probability of a person chosen is male, which is probability of M. Now, this can be calculated to be equal to R1 upon N and is equal to 120 by 200. Now, this comes from our relative frequency definition of probability, where we have the probability of the observed phenomena in the numerator and the total frequency in the denominator. Similarly, probability of a person having preference for white chocolate could be calculated as PWC, which is how we denote white chocolate, is equal to C1 by N, and this comes out to be equal to 80 upon 200. Now here, since the marginal probabilities are unknown, we make use of the marginal frequencies available from the sample data. I am sure you know that from the theorems of probability, that probability A intersection B is equal to probability A into probability B if the events A and B are independent. Now, using this formula, we can find the probability of each cell, which is nothing but P, or the probability a person being male and having preference for white chocolate. Now, this could be calculated as probability of M intersection WC. Now, this comes out to be equal to probability M into probability WC, and this is equal to, as you can see, equal to 120 upon 200 into 80 upon 200, and on simplification, this is equal to 0.24. Now, it is important to understand here that these probabilities are calculated assuming null hypothesis is true, which is that the two classifications under consideration are independent. The expected frequency is therefore found by multiplying this probability by the total sample frequency, which is denoted as N or capital N, and is equal to 200 in our current case or in this example. Therefore, the expected frequency E of this cell is equal to, we can denote this as E11, is equal to 0.24 into 200 and is equal to 48. So this can be written as E11 is equal to R1 upon N into C1 upon N into N, and therefore on simplification this comes out to be 120 upon 200 into 80 upon 200 into 200 and is equal to 48. In general, therefore, we can write down Eij equal to Ri upon N into Cj upon N into N, and this comes out to be equal to Ri into Cj upon N, where I is 1 to 2, which is the number of rows, and j is equal to 1 to 3, the number of columns. In other words, we can say the expected frequency of any cell is found by multiplying the marginal frequencies of the corresponding row and column and then dividing this value by the total sample frequency. So we can find out similarly E12, etc. Now E12, I am sure you can see by this formula, therefore is equal to R1 into C2 upon N and is equal to 120 into 70 upon 200 is equal to 42. So likewise, the expected frequency of each cell is calculated and is written in the parenthesis in the table below. We know sum of all expected frequencies should add up to the total sample frequency. So in this table, you can see we have the observed frequencies, and in the parenthesis, we have now the expected frequencies. Now, to test the independence of two variables, we need to compare these observed and expected frequencies of each cell and find whether the difference between the two is large or small. If small, it can be attributed to sampling fluctuations, and if large, we would conclude that the two variables are not independent. In order to evaluate this difference, we compute the chi-square test statistic as we computed in our earlier section or in our earlier examples. Now, from each cell, we find the difference, then we square this difference and then divide this by the expected frequency of the corresponding cell to obtain the relative frequency. And we use it in the same formula of equation 1. So the latter most frequencies are added to obtain the required test statistics chi-square. So in our current example, chi-square comes out to be a summation over I and j, where I is from 1 to 2 and j is from 1 to 3. And the formula now is, it is Oij minus Eij whole square divided by Eij. So we get 8 square upon 48 plus 3 square upon 42 plus 5 square upon 30 and so on, plus in the end we have 5 square upon 20. Now, if you simplify and add all of them, you find the value comes out to be 5.9487. Now, in order to find the critical value, we must know the degrees of freedom, which is nothing but the number of cells whose expected frequency can be freely determined. The general formula used to determine degree of freedom is R minus 1 into C minus 1. Now, since in our illustration R is equal to 2 and C is equal to 3, therefore the degrees of freedom comes out to be 2 minus 1 into 3 minus 1 and is equal to 2. The critical value of chi-square at significance level of alpha, which could be 5 square, would come out to be chi-square at 5% and 2 degrees of freedom equal to 5.992. Now, it is important to note that the chi-square test statistics is applied only if the expected frequency of each cell is at least 5. Comparing this calculated and the critical value, we find that the calculated chi-square, which is equal to 5.9487, is less than the critical value, which is 5.991. Therefore, the null hypothesis is not rejected. Thus, we conclude that the two categorical variables, gender and preference for chocolate, are independent of each other. However, if the computed value had been greater than the critical value, it would have fallen in the rejection reason, and we would have concluded that the two attributes are not independent of each other. So, having discussed all this, now let us try to sum up what we have learned in this module. So, we have learned that this module explains the two applications of chi-square distribution that concerns goodness of fit test and test for independence of two categories. The former chi-square test finds out whether a given set of data can be looked upon as a sample drawn from a population having a specified distribution like T, chi-square, uniform, etc. In the latter example, we have seen that chi-square test determines whether the two attributes are independent of each other or they are dependent. Now, this requires preparing of a contingency table of the size R into C, where the number of rows and columns, they depend upon the number of classification of the two variables under observation. The basic methodology we have learned of the test procedure lies in determining how different the observed frequencies are from the expected frequencies when the null hypothesis is true. If the difference is large, the null hypothesis is rejected, and if it is small, it is attributed to sampling fluctuations. I am sure you know we have also learned that to apply the two tests, the expected frequency of any cell should not be less than 5. Else, we need to combine few adjacent cells, which in turn results in loss of degrees of freedom.